Chapter 7 is the study of 3 different numbering systems: decimal, binary, and hexadecimal. Decimal is my primary native language because I have 10 fingers and 10 toes. I learned to count to 10 as a little child. Binary is the basic numbering system, or the basic language of our computer, because it has ones and zeros, true, false, on and off, which is how computers represent electricity. And then hexadecimal could be considered like an intermediary language between the language that I speak and the language that the computer speaks. And so we're going to talk about the 3 different numbering systems: decimal, binary, and hexadecimal in Chapter 7. So let's start off with decimal. This is a numbering system that I should be very familiar with. And so let's just see if we can get a better understanding or refresh our memories on what we learned back in elementary school. Let's take a decimal number like 2395. This number can actually be broken up into individual digits: 2, 3, 9, and 5. 4 different distinct individual digits, and each one of the individual digits is sitting in a positional value or a place. The place of each one of the positional digits can be determined by the base, which is the decimal numbering system. The base is 10, raised to an exponent. This first exponent on the least significant digit is always a 0. And so this 9 is going to be raised to the base to the 10 to the first power. 3 is going to be sitting in the position of 10 raised to the second power, and then the 2 is in 10 raised to the third power. Anything raised to the power of 0 is 1. So 10 to the 0 is 1. I know that 10 to the first is going to be 10. 10 to the second is 100. And then finally 10 to the third is 1000. If I want to make sense of what this number 2395 means, I can take its positional value and I multiply it by the value that is sitting there. So this first one is going to be the positional value of 1 multiplied by the value that is sitting there. The second one is going to be the positional value of 10 multiplied by the value that is sitting there. The third one is going to be the positional value of 100 multiplied by 3, which is the number that is sitting in that third place. And then the last one is going to be 1000 multiplied by the number that is sitting there. So let's see. 1000 times 2 is 2000. And then this is 300. This would be 90. This would be 5 if I multiply each one of those out. And then I'm going to add those products together. And ultimately what I should get is 2,395. But you're saying to yourself, you already knew that, right? We're just trying to refresh our memories on numbering systems, basic numbering systems. So we're going to start with decimal because that is our primary language. All right, so let me ask you another question. How many digits are in the decimal numbering system? How many digits are there? Well, you would probably, hopefully you would say that there are 10 digits. If I were to ask you those questions, what are those digits? Hopefully you don't say to me 1 to 10, because 10 is not a digit, 10 is 2 digits. So hopefully your answer to that question is 0 through 9. If I count them, there are 10 of them. If I list them, we start at 0 and we work our way up to 9. That's because decimal is a 0-based numbering system that begins with 0. So speaking of counting, let's see if we can count up in this decimal numbering system. So if I'm going to count up, I'm going to begin with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have just now reached the top of my numbering system, but what happens if I wanted to add 1? Oh, I could put 10, but 10 is not a single digit. 10 is actually 2 digits. So what we're going to see happening is this is sitting in a positional value. I have reached the top of that positional value, which means that this ones place, or this first place, is going to drop to 0, and I'm going to carry the 1. So now let's count up. This would be 11, 12. If I were to continue counting in my decimal numbering system, ultimately I would get to 99. And then if I were to add 1, I'm going to move from 2 positional values. Now I have 3 positional values. So when I add 1 to this first 9 in the least significant place right here, this drops my first positional value to 0, and then I'm going to carry the 1. but 9 plus 1 is going to drop my second positional value to 0, and I'm going to carry the 1. Now I want to know if everybody agrees to me that if I go 7, 8, 9, 10, the next number is 10, which is 2 positional values. And then if I count up 97, 98, 99, 100, now I go from 2 to 3 positional values to 100. All right, so I want to keep this in mind as we move to our next numbering system, binary. All right, so in the binary numbering system, how many digits are in binary? There are 2 digits. And what are those 2 digits? They are 0 to 1. Hopefully you didn't say 1 to 2, because binary is also a zero-based numbering system. So there are 2 digits. So I'm going to take a standard binary number, take the number 1, 0, 1, 1. If you don't mind, I'm going to spread the digits out a little bit because I want to try to make sense of what this number means. Just like in the decimal numbering system, each one of these binary digits has a positional value. And one thing that I should mention is that 1011 could actually be a decimal number. So the only way that I'm going to be able to tell a decimal number from a binary number is with the use of a subscript. So because this is a binary number, I'm going to put a subscript of a 2 at the least significant digit to indicate that it's binary. All right, so let's see if we can find the positional value of each one of these digits. This is in base 2, so I'm going to write the base down. The least significant digit always starts with the value or the exponent of 0. Then I'm going to say 2 to the first, 2 to the second, and then finally 2 to the third. I would continue out if there were more digits. All right, so let's see if we can find out this first one. 2 raised to the power of 0. Anything raised to the power of 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. So this is the positional value, and this is the value that is sitting there. So I'm going to take the positional value and I'm going to multiply it by the value sitting there and see if we can make sense of this number. So we are going to have a 1 times a 1. And then the next positional value is 2 times the 1, which is the value sitting there. Then I'm going to take 4 times 0. And finally, I'm going to take an 8 times a 1. So I'm pretty sure that this is 8, this is 0, this is 2, and this is 1. So if I add each one of these values up, I'm going to get the number 11. This tells me that 1, 0, 1, 1 in binary is equivalent to 11 in decimal. I don't have to put a subscript on 11 because decimal is my native language. And if I see a number that doesn't have a subscript, I'm going to automatically assume that it is decimal, even if it has some strange numbers or characters in it. All right, so speaking of counting, let's see if we can count just like we did in our decimal. So I'm going to begin counting in binary. I'm going to go 0 and 1, and I have now reached the top of my numbering system. If I wanted to add 1 to that, I'm pretty sure, just like with my decimal numbering system, that this is sitting in a positional value. And so I'm going to move from 1 to 2 positional values. This first place is going to drop to 0, and then I'm going to carry the 1. And then I'm going to continue counting in my numbering system. The very next number is 1, 1, and I have now reached the top of my numbering system again, which means that I'm pretty sure I'm going to have to go out to 3 positional values. If I want to add 1 to this one, it is going to drop this positional value to 0, and then I'm going to carry the 1. That is going to drop this positional value to 0, and I will carry the 1. Which means if I'm counting in decimal, I go 78, 79, 1, I go 7, 8, 9, 10, which takes 2 positional values, 97, 98, 99, 100, which then goes to 3 positional values. Binary does the same. We go 0, 1, 1, 0, which drops to 2 positional values, 1, 0, 1, 1, 100, which then introduces 3 positional values. So, and one other thing that I would like to mention, in the decimal numbering system, each one of these individual place or positional values has a name. In the decimal numbering system, this first positional value is called the ones place. The second positional value is called the tens place. Then we have the hundreds place, and we have the thousands place. These are very well-named positional values because mathematicians are really good at naming things. So the positional value in a binary numbering system, this is going to be the ones place. This is actually the twos place, the fours place, and the eights place. So let's look at the third numbering system. How many digits are in the hexadecimal numbering system? There are actually 16. What are those digits? Well, we have the digits 0 through 9, but that is not 16. We already established that that's 10, which means that I need 6 more digits. So how do I represent a digit when I have just run out of what I traditionally think of as digits? And ordinary people thinking up brilliant stuff decided to use letters instead. And so we're actually going to go from 1 to 9, and then we're going to use letters. So we use the letters A through F. Now I'm going to have 16 digits. If I count them, there are 16. If I list them, we have 0 through F. So let's look at a hexadecimal number and see if we can break it down into its parts. So I'm going to write the hexadecimal number 1 F A 3 9. I'm going to put a subscript on it because there are other numbering systems. Maybe there's a base 13 numbering system that uses some of the letters of the alphabet. Maybe there's a base 36 numbering system that uses all 10 digits and all 26 letters. So I'm just going to put a subscript of 16 on this to clearly indicate that this is a hexadecimal number. As with my decimal and my binary, I am pretty sure that each one of these digits in the numbering system has a positional value. Because this is base 16, the positional value of the first one will be 16 to the 0, 16 to the first, 16 to the second, the third. Each one of the digits has a positional value. Anything raised to the power of 0 is 1. So each one of the positional values has a number associated with it. So believe it or not, this is the 1's place, the 16's place, this 256 place. So if I want to make sense of what the number is, I take its positional value and I multiply it by the value that is sitting there. So this is going to be 1 times 9. If you don't mind, I'm going to move it off a little bit so I can fit them all in. This is going to be 16 times 3 because the 3 is the one that is sitting in the 16's place. The next one is going to be 256 times A. Well, the letter A in my decimal brain, I'm not quite sure what the letter A represents, so if you don't mind, I'm going to write myself a little bit of a cheat sheet over here. All right, so these are the letters of the hexadecimal numbering system, but my cheat sheet is going to tell me that the A is actually a 10, the B is 11, the C is a 12. So I'm going to put some decimal values next to those numbers in my cheat sheet just so I can remember what each one of these individual things mean. So then I'm going to come back here and I'm going to say that the A is actually a 10. And so when I multiply the 256, I'm going to multiply it by 10. I'm going to move to my next positional value, which is 4096. I'm going to multiply that by an F, but my cheat sheet would tell me that an F is actually a 15. So I'm going to multiply it by a 15. My last one is 65,536. I'm going to multiply it by the value that is sitting there. And then I'm going to add all of these together. And ultimately, I'm going to get 65,536 plus 61,440 plus 2560 plus 48 plus 9. If I do my math right, I'm going to get 129,593 in decimal. So this tells me that the hexadecimal number 1FA39 is equivalent to the decimal number 129,593. Oh, I missed the 3 on the end of my number. So let's do counting in hexadecimal and see what happens. I'm going to come back over here to my cheat sheet for just a minute because I already have it all written out. When I get to the top of my numbering system, if I wanted to add 1, I'm pretty sure based upon what happened in decimal and binary that I'm going to go from 1 positional value to 2 positional values. So when I count, we're going to go D, E, F, and then that first positional value will go to 0. The second positional value goes to 1. And then I would have 11 and 12, and if I continued counting, ultimately this would go up to FF. And then if I were to add 1 to my FF, I'm pretty sure that I'm going to go to 3 positional values. So that first F, when I add 1 to that first F, This is going to make this positional value 0, and it's going to carry over that 1 to the next place, but f plus 1 is also going to put that positional value to 0 and carry over to 1. So if I were counting in hexadecimal, we would go A, B, C, D, E, F, 1, 0, 11, 12, 13, all the way up to FA, FB, FC, FD, FE, FF, 100. 101, 102, 103, and so on. That is counting in hexadecimal. So I can see that a 1FA39 in hexadecimal is equivalent to a 129,593 in decimal. But these actually represent the same value. So let's say, for instance, that I had 10 apples that I put on a table in front of me, and surrounding that table I put 3 people. One person is a human that has 10 fingers and speaks in decimal. One is an alien that has 2 fingers and speaks in binary. And the third person at the table is an alien who has 8 fingers on each hand and speaks in hexadecimal. And I would ask each of the 3 of them, how many apples are on the table? The human would hold up their fingers and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They would say there's 10 apples on the table. The alien with 8 fingers on each hand that speaks hexadecimal would say there are 1, 2, 3, 4, 5, 6, 7, 8, 9, A. There are A apples on the table. And the third alien with the 2 fingers would count in binary. And he would say there is 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, I think I've just lost count. I know that a binary 10 is 1, 0, 1, 0. So my binary alien would say there are 10 apples on the table. Does that actually change the number on the tables? Because my binary alien says there are 10. My hexadecimal alien says there are 8. And my decimal alien says there are 10 apples on the table. It doesn't change the number of apples on the table. It just changes the way that we represent them based upon the language or the numbering system that we used. So next we need to find out about converting between the 3 different numbering systems, and that will come in the next video.